So now how do we work on a normal distribution that is no longer a standard normal distribution? And in other words, I call this type of normal distribution some general normal distribution. Meaning, we will no longer use the random variable z, but instead we are using the random variable x. Some random variable x to represent our population data, a continuous random variable. And symbolically, our continuous random variable is distributed normally. That's what the n is for. But now our mean and standard deviation no longer at 0 and 1. We're now at some mean, given mean, and some standard deviation. So remind yourself, once again, mean is given, as well as sigma, the population standard deviation, is also given. And our bell curve is going to look like this. We have a horizontal axis having all different values of our random variable x. And our bell curve is a nice PVC with a bell-shaped curve. And the mean value is, once again, remind yourself, exactly in the middle. And we won't trivially see how the standard deviation being displayed in this graph. However, we can always note the given value of the sigma of the standard deviation somewhere near our curve. So now that even though we're no longer working on a standard normal distribution, but on a general normal distribution like this, one fundamental from the standard normal distribution can be carried over here. Let's say on our general normal distribution, we have a value x equals a as being some value on our horizontal axis here. The fundamental I'm talking about is that from anywhere we have a value of the random variable x, there will be a cumulative area on the bell curve shaded to the left-hand side. We can always find that cumulative area. And once again, if this was a standard normal distribution curve, and I would call this the left area, or the area to the left of x equals a. And so the same way here, now we are working on a general normal distribution. This is also an area to the left, or an area left of x equals a. And symbolically speaking, this area shaded to the left-hand side is the same as the probability on this bell curve, on this normal distribution, that we're going to find a value of x being less than or equals to a. And it would be the same if we're skipping the equality sign. So probability where x is strictly below a, any one of these two symbolic statements brings up that area shaded to the left-hand side of x equals a, and the answer will turn out the same. And the way how we get it done will also be the same. As a quick example to illustrate the general formulation of this method when we're working on a general normal distribution, then let's look at this example here. On this example, we are given a continuous random variable that is distributed normally with a mean at 3 and standard deviation 0.25. So apparently this normal distribution is no longer a standard normal distribution, but we will definitely have a bell curve. So once again, I highly recommend draw the bell curve anytime we're working with a normal distribution. So this time my line at the middle is 3, and the sigma population standard deviation is 0.25, and the random variable x is being labeled on my horizontal axis here. And let's say now we are I'm going to look at a value being 3.45. And so the question in this quick example I'm given here is, let's find the probability that on this bell curve we are looking at having a value of x being less than or equals to 3.45. And as I said earlier, having equal signs or without having equal sign will not change the way how we do the problem and won't even change the final answer. The first thing I'm going to be doing from where my value, and here's the shading on the bell curve that represents the area that represents the value less than or equals 3.45. And so once again, this symbolic statement translates into an area to the left of 3.45. So to begin with a problem like this, I am going to 3.45 from where my value stands on the bell curve. I am going to subtract 3 and divide by 0.25. So have a moment to observe this calculation here. But what we realize here is this calculation is nothing but to find the z-score of our value 3.45. So 3.45 is a value but on the non-standard, on the general normal distribution. Then what we did here is we found the z-score correspondingly of 3.45. So this z-score calculation comes out being positive 1.8. Once we found z-score, the argument here is that this probability on the general normal distribution curve when x falling below or equals 3.45, once we found z-score, this probability is equal to that probability on the equivalent standard normal distribution where z-score is less than or equals 1.8. And that is the major connection between any general normal distribution and the standard normal distribution. And once we clearly realize that this problem is the same as the equivalence version on the standard normal distribution curve, we're looking at z-score less than or equals 1.8, then we can once again imagine for ourselves that we have a bell curve with center at 0, with standard deviation 1, and this bell curve, on this bell curve we're finding that area shaded to the left of 1.8. And now that area can be found by, I talked about my tool to calculate area left on a standard normal distribution. So here I'm going to run my LSND program, providing z-score 1.8. And that will get me my answer. So calculation comes out to be rounded to 4 decimal places, 0.9641. So this answer is the answer that on our standard normal distribution we have the area shaded to the left hand side at 1.8. But also this answer is the same as the answer that on our general normal distribution we have the area being shaded to the left of 3.45. Or symbolically, this is how the two statements are written. And so, as a generality that we have learned after the quick example, then here is a general normal distribution. And at some value of the random variable x equals a, we will always have an area shaded to the left-hand side. So this value a, respectively to our continuous random variable x, but only some general random variable x. Then from where A stands, there will be a corresponding z-score, and we can find that by z equals our value minus the mean, and we're dividing by the standard deviation. And so this z-score is the z-score of our value x equals a. Once we found our z-score of our designated value a, then the fundamental connection between any of our general normal distribution with the standard normal distribution is that this area shaded to the left-hand side of our general normal distribution will be exactly the same area, the same probability, where as on our standard normal distribution, with the area being less than or equals the equivalent z-score that we calculated. Or in other words, I'm attempting to make an equivalent picture over here, but this area on our normal distribution, general normal distribution curve, is equivalent or corresponding to some area on the standard normal distribution. This is now the n 0, 1, and the value x generally here has a corresponding z-score, let's say some z-score lowercase z. And the two areas here are fundamentally equal value. And once we recognize that connection, that our area generally shaded on any general normal distribution has a corresponding area on the standard normal distribution being exactly equal value, then from here we can go ahead and run our LSND. And as I explained in my earlier lecture, that LSND is only my program, but there are many other web programs out there, or web resources, web tools out there, allows you to find the area to the left of a z-score. And that's how we're finding the area to the left for any of our value on a general normal distribution. Now, at this point of this lecture right here, and at least within this video lesson here, I must apologize to viewers out there outside of my statistics class. But in these days, since technology became so powerful, I do admit that there are plenty of calculator as well as computer programs that handles directly the area on any general normal distribution curve, and completely skipping finding z-score. But for students in my class, I would like to maintain the usefulness. I would like to maintain in their understanding the usefulness of z-score, and I would like to maintain for my students this fundamental correspondence between any general normal distribution and a standard normal distribution. That is the reason why in this video lesson I will never mention how to use those other technologies out there that handle this area in only one button. But any of my later examples that you will see will always show the step where we have to find z-score for any of our value from a general normal distribution. Then from there we are going to run, the only tool here is to find the area to the left of any specific designated z-score. Then we will implement that answer, the answer of the area to the left of a z-score on the standard normal distribution. We will implement that answer to various different problems on any general normal distribution. Now, LSND is only my program that I wrote, and recall from the other video lessons I discussed about the LSND. It's only intent to find the area to the left on any standard normal distribution of a specific given z-score. And so you don't have to use this program of mine. There are plenty other web resources, web tools, or even calculator programs that can also do the similar functionality can find. But basically here we only look for the area to the left of a designated z-score on the standard normal distribution. then we're going to use that answer to find, we're going to be using that value to implement into other type of problem on a normal distribution.